This is Dr. C. Lakshmipati, Associate Professor of Physics, HNS Department, SRIT Engineering College, Anantapuram. Today we are discussing fourth unit, that is quantum mechanics and free electron theory. So, the quantum mechanics and free electron theory, we have the topics wave particle dual nature. That means the particle having the wave matters having the particle nature and wave nature. Next, de Broglie hypothesis. It is described the matter waves, that is particle nature and wave natures. And he also described the wavelength, de Broglie wavelength, that is lambda equal to h by p, that equal to h by mv. Next, we have the derivation of de Broglie wavelength. From the Planck's theory, E equal to h nu. Then Einstein mass energy theory, we have the m equal to E equal to mc square. Next, from the equation 1 and 2, we have h nu equal to mc square. Then we have the hc by lambda equal to mc square. Here nu equal to c by lambda. Therefore, then we get the lambda equal to hc by mc square. Next, lambda equal to h by mc. Here, m is the mass of the particle, c is the velocity of light, h is the Planck constant. So, mass into velocity is nothing but a momentum. Therefore, lambda equal to h by p or h by mv. This is the de Broglie wavelength equation. Next, we have the de Broglie wavelength in terms of energy. That is, we know the kinetic energy equal to half mv square, and multiplying with the mass on both sides, we get Em equal to half mv square, m square v square. M square v square equal to 2 Em. Then square root of m square v square, that equal to square root of 2 Em. Finally, mv equal to square root of 2 Em. Then we get the momentum lambda equal to h by square root of 2 Em. So then de Broglie wavelength is associated with an electron, that lambda equal to h by square root of 2 MeV. Then here Planck constant, mass of electron and charge of electron, substituting in this equation, we get finally 12.26 by root V angstrom unit. Then properties of wave matter. Lighter is the particle, greater the wavelength of associated particle. Next, when V equal to 0, lambda equal to infinity, that wave becomes okay undetermined. And if V equal to infinity, lambda equal to 0, this shows that matter waves are generated by the motion of the particles. Lambda equal to h by mv is independent of charge. This shows that these waves are not electromagnetic waves. So velocity of matter waves is depends on the velocity of particles. The wave velocity of matter waves is greater than the velocity of light, that equal to u equal to c square by v. Next, we have the wave function, that so a variable quantity which characterizes de Broglie waves is known as wave function. So physical significance of the wave functions, the wave function has no physical meaning. So it is a complex quantity representing the matter waves of a particle. Modulus of psi square is real and positive. Amplitude may be positive or negative, but the intensity is always real and positive. So, modulus of psi square represents the probability density, or probability of finding the particle in the given region. For a given value, d tau, probability p equal to, so triple integral of modulus psi square d tau. So here d tau equal to dx dy dz. Then the probability value lies between the 0 and 1. Triple integral of modulus psi square d tau equal to 1. This wave function is called normalized wave function. Okay, Schrodinger wave equation. Schrodinger derived an equation for the wave matters is known as Schrodinger wave equation. There are two types of wave equations are there: time independent wave equation, and second one, time dependent wave equation. So in this one, time dependent wave equation and time independent wave equation. That wave equation are derived, and finally we get what is that dou square psi by dou x square equal to minus 8 pi square m by h cut square into E minus V. And finally, we get dou square psi by dx square plus 2m by h cut square into E minus V into psi equal to 0. This equation indicates what is that Schrodinger wave equation. Finally, we can write del square psi plus 2m by h cut square into E minus V into psi equal to 0. This wave equation is known as Schrodinger time independent wave equation. Particle in a one-dimensional box. Consider a particle of mass m moving back and forth inside a potential box of infinite height and length shown in the figure. So in the particle, as the particle is moving freely inside the box, it is associated with a wave and its position is represented by a wave function psi. So boundary conditions are V of x equal to 0 when x less than a, where psi not equal to 0. V of x equal to infinity when 0 greater than or equal to x greater than or equal to a, where psi equal to 0. Then we get after derivation, then we get the wave function according to Schrodinger time independent wave equation. Then here v equal to 0, then we get d square psi by dx square plus 8 pi square m by h cut square e psi equal to 0. Next we get the, finally we can consider the wave equation conditions or applying the boundary conditions. Then we get the wave equation function psi n equal to a sin n pi by a into x. Then we get the particle in one dimensional box, the energy level of the nth level En equal to n square h square by 8m a square. Suppose where n equal to 1, 2, 3, comma and so on. So suppose n equal to 1, En equal to h square by 8m square and n equal to, then E2 equal to 4h square by 8m square and E3 equal to, we get 9h square by 8m square. Then finally we get what is that normalization of the wave function. In the normalization of the wave function, we can integrating the wave function equation. Integration 0 to a square sine square n pi x by a dx equal to 1. Then after solving this one, we get the wave function conditions. Then the wave function shown in the figure. So psi n equal to square root of 2 by a into sine n pi x by a. We get the wave function, particle wave function. Then the diagram shown in the figure. Next, class, classical free electron theory of metals. So here, Drude-Lagrange will be proposed a theory for free electrons that is known as classical free electron theory. So according to classical free electron theory, in metals, there are a large number of free electrons moving freely in all possible directions. So here, gas molecules in a container obeying the laws of kinetic theory gases. In the absence of electric field, the energy associated with each electron to a temperature T is given by 3 by 2 kT. Then it is equal to the kinetic energy of the particle. Next, here we have the freely moving electron collide with the other positive ions or other particles. Next, the electrons velocity in a metal obeys the Maxwell-Boltzmann distribution of velocities. The free electrons move in a constant potential field. Then, when an electron field is applied to a metal, free electrons are accelerated in the direction of opposite to the direction of the applied field with a velocity called drift velocity, represented by Vd. Then electrical conductivity. So let us consider a conductor of length L and area is A. Then volume is equal to AL. Then from that the number of electrons is N. Then the total number of electrons in the metal is ALN. Then the charge in the material is ALNE. Then the current I equal to charge by time Q by T, that equal to ALNE by T. Then we get here L by T equal to Vd, then I equal to A N E Vd. Therefore, Vd equal to I by Ne, that equal to I by A equal to J by Ne. So J is the current density, that equal to I by A. So then we get what is the current density J equal to Ne Vd. We know that. Then the electric field will be excess some, apply the some force on the electrons, that is F equal to small e into capital E. But according to Newton's second law, F equal to Ma. So both equations are equal. Ma equal to small e into capital E. A equal to small e capital E by M. After solving, we get the conductivity formula sigma equal to Ne mu. Next, according to what is that free electron theory, according to RMS velocity, the conductivity will be get sigma equal to n lambda e square by square root of 3m kt. And merits and demerits. Merits, it verifies the Ohm's law and it explains the electrical and thermal conductivity, derives the Weidmann-Franz law, and it explains the optical properties of metals. Demerits, it fails to explain the electrical conductivity and in semiconductors and insulators. It fails the explanation of temperature variation of electrical conductivity. Next, fails to explain the concept of specific heat of metals. So it fails to explain the mean free path of electrons. Next, quantum free electron theory. So to overcome the classical free electron theory, then Sommerfeld proposed a theory is known as quantum free electron theory in 1928. So assuming that the valency electrons moves freely a constant velocity within the boundaries of metal and it prevent from the escaping the metal at the boundaries. Hence, the electrons is trapped in a potential well. The distribution of electrons in various allowed energy levels occurs as per Pauli's exclusion principle. The attraction between the free electrons and the lattice ions and the repulsive between the electrons themselves are ignored. So the distribution of energy among the free electrons according to Fermi-Dirac distribution statistics. The energy values of free electrons are quantized. Next, quantum free electrical conductivity. So from here also we can derive the electrical conductivity equation according to quantum free electron theory. Then we get what is the sigma equal to n e square tau f by m star. Next, merits. It successfully explained the electrical and thermal conductivity of metals. It can be explained the thermodynamic phenomena. It explains the temperature dependent of conductivity of metals. It can explain the specificity of metals. It can explain the magnetic susceptibility of metals. It can be explained the photoelectric effect, Compton effect, and black body radiation. It gives the correct mag- mathematical expression for the thermal conductivity of metals. Demerits. It is unable to explain the metallic properties exhibited by only certain crystals. It is unable to explain why the atomic arrays in metallic crystals refer certain structures only. This theory fails to distinguish between the metals, semiconductor metals, and insulators. It fails to explain the positive value of Hall coefficient. So, here also, according to the theory, only two electrons are present in the Fermi level and they are responsible for conduction, which is not true. Okay, Fermi Dirac distribution. Here, in a metal, absence of electric field, free electrons moves at random. So, similar to the behavior of electron gas, since electrons are indistinguishable particles and have spin, they are known as the fermions or Fermi particles. Hence, such a electron gas obeys the Fermi Dirac static distribution. So, it can be explained the equation f of E equal to 1 by 1 plus exponential E plus EF by kT. So, here the effect of temperature on Fermi Dirac distribution function, the conditions are there, three conditions. One is f of E For E less than E of at T equal to 0 Kelvin, then F of E get 1. That means 100% of electron will be occupied the Fermi energy level. Next, second condition, what is that? F of E, that means E greater than EF at T equal to 0 Kelvin, then F of E get 0. That means 0 electrons will be occupied at the Fermi energy level. Next, f of E equal to E of at F, T equal to 0 Kelvin, f of E equal to 1 by 2. That means it will be obeys the acceptable electrons will be occupied the 50% of the Fermi energy levels. Source of electrical resistance. There are three types of sources are there. Lattice vibrations by the impurities, by the structural impropers. So, which are discussed in the origin of energy bands next. So, how to form the energy bands in the material or atoms or material. Okay, there will be it will be combined the energy levels and forms the band. That band will be divided into two forms, that is conduction band and valence band. The gap between the conduction band and valence band is known as energy band gap. Then classifications of solid. There are according to basis of magnitude of forbidden band, there are three types of solids are there, which is conductors, semiconductors, and insulators. So semiconductors means which allow the flow of current partially or moderately. Then it is called semiconductor material. Then the energy level will be moderate and the value will be 0.7 electron volts to, that is say in germanium, and silicon 1.1 electron volts. Example, germanium silicon. Next, insulator. Which material does not allow the flow of current in the material is known as insulators. The band gap will be very high. Then difference between the conductors, semiconductors and insulators are shown in the table. Okay, in this chapter we discuss about what is that quantum mechanics and free electron theory. In quantum mechanics, de Broglie wavelength and associated with the electron and Schrodinger time independent wave equation, and we have the potential one dimensional potential box and classical free electron theory, quantum free electron theory, and we have the Fermi Dirac distribution function and energy. Next we have the finally origin of energy bands and classifications of solids. Okay, thank you.